Good morning. My name is Manikant. I am from Institute of Aeronautical Engineering. Going to say about a topic of boundary layer separation, which is belonging to the course of aerodynamics. So let us go to the topic boundary layer separation. The name itself says that the layer separation of a boundary. It's a boundary related to a surface or any other object that such as airfoil in our aerodynamics and in other objects such as if we compare a car, it's a body of it. If we compare a ball, then it's a surface of the tennis ball. If we say the hair or cork ball is a hard surface. So there are, that is known as a boundary and the layer formed by the airflow and its separation. We are going to talk about that one. So flow or a boundary layer separation or a flow separation is a detachment of a boundary layer from a surface into a wake. So it is going to divide. I mean, it's going to separate the flow. I mean, the flow around the boundary layer, and it is going to be awake. Okay. Separation occurs in a flow that is slowing down. So separation occurs only when this flow is going to be slowed down. I mean, if you see an airfoil, the flow will be slowed. Let us go to the next picture. I will be showing you there what is the flow slowing down. With pressure increasing after and passing the thickest part of the streamlined body or passing through a widening passage. Flowing against an increasing pressure is known as flowing in an adhesive pressure gradient. The boundary layer separates when it has a travel far enough in an adhesive pressure gradient, that is the speed of the boundary layer relative to the surface has stopped and reversed direction. So here we are talking about adhesive pressure gradient. So the adhesive pressure gradient is a pressure gradient developed to increase the drag or it stops the airflow. I mean the body. I mean the body or a such as the body means an airfoil or any ball or any object. So it stops and it increases the drag. So that is known as the pressure drag, and the pressure drag is due to the flow separation occurred in it. So it's just due to a boundary layer separation. I'll be going to show in later in a deep pictorial way. The flow becomes detached from the surface and instead takes the form of eddies and vortices. The fluid exerts a constant pressure on the surface once it has been separated instead of continuously increasing pressure if still attached. So here, it states the point that when the flow, I mean, get out the path. I mean, if we go out of the surface of that thing, so it says that they are forming eddies and vortices. So the flow exerts a constant pressure on the surface once it has been separated instead of continuously increasing pressure and it is still attached. If it is still attached, then the separation goes on and it increases pressure. So see here, this is the one which explains a deep pictorial way. So go to the picture, you can see that the flow of an airfoil and there are the vortices, they are forming some vortices here, right? So these are the vortices forming. If you see this, the flow, I mean, on this airfoil, the air moves about this, I mean, around this upward direction, and thereafter, it due to the thickness cut, and it has a free here. It has a freedom here, and it comes degree of freedom increases here, and so it comes here, and thereafter it forms some eddies or some vortices, and thereafter it increases the pressure here. So due to this pressure increment, so there is a pressure drag occurring here. So this pressure drag decreases the lift. So the lift occurred to an airfoil will be decreased due to this pressure drag and this boundary layers. This is known as a boundary layer separation. So actually, this is the boundary layer. So if you go downwards, so let me show with the annotation. So see this. This is known as a boundary layer which is not yet separated. This is known as not separated one. And if you go to this, this is known as a separated one. So this is the part separated one from here. So until here it's good, until here it's good, until here it's good, and thereafter it was been separated and it forms some eddies like this, and these are the eddies formed and these are vortices formed here. So that's the thing. So that's the thing happened here just now. So in aerodynamics, flow separation results in reduced lift. So as I said, the flow separation results in reduced lift and increased pressure drag, causing the pressure differential between the front and the rear surfaces of the object. See this. This is the one happening here. So your front, it is low pressure, and here is the high pressure. Actually, it increases some thrust, but it's very minimum and it's negligible. And but the main thing it does is it decreases the lift. It decreases a huge lift. So due to this pressure here, upward direction, and the lift will be acting in this direction. So it decreases the thing. So since the lift acts like this, so lift acts in this direction, and the pressure is acting in this direction. The maximum component of this one will be like this in this direction, and so it will be reducing the what we say, the lift. So that's the problem. So it causes buffeting of aircraft structures and control surfaces in internal passage of separation until the stalling, and causes stalling and vibrations in machinery bleeding, and increases losses in inlets and compressors. So one of the biggest advantages is this due to the boundary layer separation. So it reduces the lift, and it also gives a chance to stall. I mean, upon increasing the lift, if we increase the angle of attack, of course, the boundary layers separation goes on, and then it causes a problem for us. So it reduces the lift, and also due to the huge reducing lift sudden lift reduction, it we can say that it has a stall. So and vibrations in machinery will be more due to this boundary layer separation. So what shall we do now? If this continues, I mean, there is a huge disadvantage of this one. So what can we make this one as an advantage? And I mean, we can decrease the separation point. So if we decrease the separation point, we can achieve a great thing. So that is just research on, the research are going on how to decrease the, I mean, boundary layer separation. So the researchers have gone into the design of aerodynamics and hydrodynamic surfaces, countering and adding features which delay flow separation and keep the flow attached for as soon as possible. So this is an example. This is, I think that you know this. This is a golf ball, and normal a plastic, I mean, normal a ball which was used in a past tense. So let us consider that this is a golf ball. One side is golf, and other part is some plain ball. It's related to golf, but it's plain. So golf balls has some n number of holes. I mean, it has punches. So see this here. Here, if you see this, without punches, the boundary layer started from here. This is a separation point occurred here. This from this part, it increases the separation, and here the pressure increases a huge manner. And this is the width. I mean, this is the wake happening here, the wide wake. And coming to here, if you go this one, you will coming to the golf ball, which has punches. So the separation point is here. So it's maximum distance. So this is the place. So this is this much difference between this. So this difference is being reduced. So this, I mean, we can reduce this much. So this is the idea which has been got out from the research. And this is one kept for the golf ball. And it's a very great idea that way. Got it. So this is a separation point for a normal ball, and this is a separation point for the golf ball. So researchers have gone into this design, and hydrodynamically and aerodynamically they have kept this flow separation, and it's wonderful design. And the main role occurs in our daily conditions, such as if you go through the airfoil is a main example, where we can say that there are many disadvantages if in with the body layer separation, and that's it.